Greetings and welcome to the Chemistry 222 Exam 2 review. We're going to go through some questions which you might see in the upcoming second midterm exam. And the second midterm exam will be over chapters 9, 10, and 11. So chapter 9 was basically about the gas laws and things you can do with gases. Chapter 10 looked at liquids and solids, how to interconvert between the different phases, vapor pressure, stuff like that. And chapter 11 was on solutions, the colligative properties, the new kinds of concentration units, all that kind of stuff. If this class is an online class where we're not meeting face-to-face, then the midterm exam will have 20 multiple choice questions and you'll have 3 to 4 short answer questions. And you should complete the exam once it comes out. Make sure you use my form and email it to me by Friday at 9 a.m. And when I return your exam to you, your corrected exam, in addition to the score, you'll also get a summary sheet at the very end, which is basically telling how you're doing in the class as of this day. And I encourage you to check out the summary sheet to make sure all your labs are turned in, that kind of stuff, no big deal. Now, if this is the class you're taking right now is a face-to-face class, then we will talk about all of the requirements and what to expect during the class lectures themselves. But regardless of whether your class is face-to-face or online, if you do have questions on any of this, I do want you to email me. I know it can be kind of crazy and kind of confusing, and if you don't know what kind of class you have or you're uncertain as to the protocol, definitely reach out to me and I'm more than happy to help. Okay? Good luck with your studying. I know you can do this stuff, and hopefully by going through this review, you'll be that much more prepared. So without further ado, let's start the review. In a normal face-to-face class, this would be an iClicker exam review. And so what I would do is present a question like this one right here. I would give the students a few moments to kind of think about what the answer should be. They could enter their answer into the iClicker system, and then we talk about the actual answer once most people had responded. And they get extra credit and stuff like that way. Well, in this version of the exam review where it's on a video, I don't have a mechanism to grant extra credit opportunities, so I'm very sorry. But what I will do is I'll announce the question. I'll give you a few minutes to work on it. There'll be a place where I'll say pause the video, and I encourage you to pause it, work on the question, and when you're ready, you can unpause the video and we'll talk about the actual answer. You can see how you did. And again, this is for your information only. All right, I don't mind if you get all the questions wrong. I bet then that you have a lot you're learning a lot while you're going through the questions, and that's kind of the goal of these problems. So anyway, this is the first of these questions. A sample of gas has a volume of 222 milliliters at 695 millimeters of mercury and 0 degrees Celsius. And the question is, what should be the volume at the same sample of gas if it were measured at 333 millimeters of mercury and 0 degrees Celsius? So see if you can work on this question. Pause the video and you can work on it. And when you're ready, you can unpause it. We'll talk about the answer. Pause the video now. Okay, at this point, I'm assuming you've had enough time to work on the problem and you want to see how you did. So without further ado, let's get into it. This is an example of when you have more than one quantity changing in a gas, and there's different ways to approach it. One way would be to try to see specifically like which ones are changing. And if you look at this problem, the pressure is 695 millimeters of mercury initially, and it ends up being 333 millimeters of mercury, so it's certainly changing. The temperature is listed, but the temperature is the same. So really, temperature doesn't play a part here. It's not as important. On the other hand, you start with this volume, and the question is, what is the new volume? So there's a couple ways you could do this, and one way would be to use P1 V1 equals P2 V2. And if only pressure and volume change, which is all that's happening right here, you can leave the units as they are. You just want to make sure the pressures are the same kind of units and the volumes are the same kind of units. So you don't have to use atmospheres for pressure and liters for volume if it's just P1 V1 equals P2 V2. Remember that if you have a temperature change, you must use Kelvin. You don't want to divide or multiply by 0. 0, that would make things really messy. Another way to do this problem, and what I kind of use more and more, is I go back to the ideal gas law. P and V are changing, but everything else, nRT, is the same. So what that means is if I have a P1, V1 set of conditions, that's going to equal P2, V2, because again, N, R, and T are not changing. Those are all a constant. So by hook or by crook, find out that P1 and V1 equals P2, V2. It doesn't matter how you do it. We want to solve for V2. And so V2 equals P1, V1 divided by P2. And again, you can literally put those numbers in just as they are. And if you do that, you should get 463 milliliters, the new volume. Again, you don't really have to use the temperatures down there. I included P1, V1 over T1 equals P2, V2 over T2. And I did that because I wanted to remind everyone, you must use Kelvin, don't use Celsius. All right, that's like a big time bad boy. And again, you don't have to convert to liters and atmospheres either. You can just leave them as milliliters and millimeters of mercury. Pressure and volume, if you will, are a bit more flexible. Finally, the final answer, negative 155 milliliters, doesn't make any sense. Volume should always be a positive number. It's three-dimensional space. Negative volume is fun for science fiction people like me, but not really very helpful in a science world. Gas density. Which has the greatest density at 25 degrees Celsius and 1 atmosphere of pressure? We're going to assume that these are all gases, and I'd like you to try and figure out which one has the greatest density at those set of conditions. This is a good place to pause the video. You can work on the problem, and when you're ready, you can unpause the video. We'll talk about the answer. Pause the video now. Okay, at this point, I'm assuming you've tried the problem and you want to check out your answer, see how you did, so let's get into it. If you remember, one of the other ideal gas laws, not the PV equals nRT, but the other one which is kind of helpful, PM equals DRT. I called this the evening dirt equation, which is totally silly, but it maybe helps you remember. The important thing for us here is that this equation does show how the density of a gas, the D part right there, relates to the M, which is the molar mass of the gas. So in a sense, when it comes to gases, the heaviest molar mass, the biggest molar mass, will have the biggest density. So what you want to do on that list is go through and find out the molar masses of each one of those gases. So for example, oxygen, O2, has 2 oxygens, so 2 times 16 on the periodic table, about 32 grams per mole. Nitrogen, the next one, has 28 grams per mole, 2 times 14. So we would say that O2 has a bigger density than N2 because it has a bigger molar mass. You can go through that list. H2 is smaller than O2, 2 grams per mole. CO2 is bigger than O2. It's about 44 grams per mole. So CO2 would be more dense than oxygen at those conditions. However, the biggest molar mass of all belongs to xenon. Xenon on the periodic table, which is a noble gas, 131 grams per mole. So bigger molar mass, bigger density. We would say that xenon has the biggest gas density at those conditions in this list. Diborane, which is B2H6, reacts with oxygen to give boric oxide, B2O3, and some water. If 1.5 liters of diborane, is mixed with oxygen, what volume of oxygen is required for the reaction? And assume constant temperature and pressure. See if you can solve this problem on your own by pausing the video, working on it, and when you're ready, you can unpause the video. Pause the video now. Okay, I'm assuming you've worked on the problem and you want to discuss the answer, so without further ado, let's do it. Instead of liters of diborane, let's assume that this question said if 1.5 moles of diborane is mixed with oxygen, how many moles of O2 would you need? Well, in the old days, we would have seen that there's a 1 mole B2H6 to 3 moles O2 ratio. So if we had 1.5 moles, we would multiply 1.5 moles by a 3/1 ratio. That converts moles of diborane to moles of oxygen, and 1.5 times 3 would be 4.5 moles. All right, that's if this question was moles. But obviously this question is liters. All right, one method you could use to solve this particular problem is you could take the liters, you could assume, say it was STP, standard temperature and pressure, and you could use that to find moles of diborane. You'd multiply by 3 to get moles of oxygen, and you'd use the same recommendations that you used earlier to find the volume of O2. And that would be a lot of work, but you could do it. But another way you can do this problem is to go back to ideal gas law. PV equals nRT, all right? And I want you to focus on the V and the N, all right? It says that the pressure and the temperature are constant, and R is, of course, a constant. So notice that volume and moles are on opposite sides. That means they are proportional to each other. So as one goes up, the other one goes up. If one goes down, the other one goes down, all right? Moles, if moles goes up, then volume goes up, and if moles goes down, volume goes down. It doesn't make as much sense for volume to go down and moles to go down because that's quantity of mass. But anyway, I digress. In this problem, the liters are the same as moles in how they work in this kind of problem mathematically. So if 1.5 moles of diborane needed 4.5 moles of oxygen, 1.5 liters times 3/1 will give you the equivalent answer in terms of liters of O2 for this stoichiometry. So 4.5 liters of oxygen is correct. And we can do the 3-to-1 stoichiometry because moles and volume are also proportional to each other. So just like we use 3-to-1 mole ratio, here we're going to use 3-to-1 volume ratio. So it should take 4.5 liters of oxygen to react with 1.5 liters of diborane. You can do this kind of problem as well with pressure if you assume that temperature and volume are constant. So that's kind of a powerful technique sometimes to use. This is a lot easier than trying to go through the ideal gas law, etc., etc. Diborane, again burning in air, same equation as before. There are 3 gases in this reaction. So diborane, B2H6, oxygen, and water. I'd like you to place these gases in order of increasing velocity, i.e. from slowest gas to fastest gas. See if you can figure this answer out. If you need to, pause the video. When you're ready, unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming that you've worked on the problem and you want to talk about it, so let's do so. When it comes to the speed of gases, as long as they're all at the same temperature, and for a reaction like this, that would be a very fair statement to make, then what it means is that the smallest molar mass will be the fastest, and the biggest molar mass will be the slowest, all right? So for this problem, what you want to do is put the B2H6, 3O2, and water in terms of molar mass, all right? So water is about 18 grams per mole when you figure out its molar mass. O2 is about 32 grams per mole. So because water has a smaller molar mass, it should be fastest, and oxygen with the bigger molar mass would be smaller. B2H6 has 2 borons, which are about 11 grams per mole each. That's 22, plus another 6 or so for the hydrogen. B2H6 is going to be about 28 grams per mole, and that falls in the middle of water and oxygen. So if we want these in order of increasing velocity, we want the biggest one first, and I believe that's going to be O2. And then B2H6 is a molar mass in the middle, so that would be the middle speed. And water, with the smaller molar mass, water should have the fastest speed. So it goes O2, B2H6, H2O. And there's the molar masses. So you can see it went from heaviest molar mass to smallest molar mass. Chemists can use molar mass in lots of different ways, and this is just one example to see which one are going to have the fastest speed. Equal masses of helium and neon are placed in separate containers of equal volume at the same temperature. Compare the pressure of the gases, all right? And you might be tempted to automatically put D, too much pressure, science, but trust me, that's not the right answer here. So anyway, equal masses of helium and neon. See if you can figure out which one of those is the correct answer. I recommend pausing the video. You can work on it, and when you're ready to talk about the answer, unpause it. We'll talk about the answer. Pause the video now. I'm going to assume you've worked on the problem and you're ready to talk about the answer. So without further ado, let's get into it. The key to figuring this question out is to understand what pressure is. And pressure is about collisions with walls of the container, or pressure is about collisions with molecules with each other. Pressure is proportional to moles. And I know that because PV equals nRT. So P and V are on opposite sides. As the moles goes up, the pressure goes up. So what we want to do here is, because we have equal masses, is just pick some mass, all right? And I would like to pick 4 grams. Now you can pick 1,000 grams, 10 to the minus 7th grams, whatever number you want. But for me here, it's going to be easiest to think about 4. I'm doing that because I want to figure out how many moles of helium and neon we would have if we had 4 grams of each gas. Now 4 grams divided by 4 grams per mole, which is the molar mass of helium, that means 1 mole of helium. Now neon, on the other hand, is about 20 grams per mole if you look it up on the periodic table. So 4 grams, same mass as helium, divided by 20 grams per mole. This is going to be about 4/20ths, 2/10ths, all right, 1/5. This would be about 0.20 moles of neon. So notice that the moles of neon are less than the moles of helium. And you can pick any number you want. You don't have to pick 4, but you're always going to get this. The moles of neon are less than the moles of helium. And that's because the molar mass of the two substances is different. Well, fewer moles means less pressure. So we would expect, because there are more moles of helium, we would have a greater pressure of helium. We would expect the pressure of helium to be greater than the pressure of neon because there's more moles. So there's formally what I tried to do in the upper right hand corner. You end up with less moles of neon, which is less molecules running around colliding with each other. You have more molecules, or atoms I should say, of helium running around, so they collide with each other, more pressure. Pretty interesting use there. But you can see how if it says equal masses, just pick some number, any number, whatever's easier, and then figure out the moles, and from moles you can figure out pressures, stuff like that. This question involves intermolecular forces. So using the IM forces, put these in the predicted order of decreasing boiling points, all right? So decreasing boiling points. So probably what you want to do here is, first of all, figure out of the 3 substances listed, which one has the strongest intermolecular forces and then the weaker intermolecular forces. If you have a tie, then usually bigger molar mass substances will have higher boiling points than the lower ones. This is a good place to pause the video, maybe think about it a little bit, and when you're ready to talk about the answer, unpause it. We'll do so. Pause your video now. Okay, I'm going to assume you've had time to work on it and you want to talk about the answer, so let's do so. So this question, what I said earlier, is I would first find the intermolecular forces working on the substance and then compare those. And sometimes that will be all you need. Some intermolecular forces are stronger than others. So like dipole-dipole is stronger than induced-dipole-induced dipole, but hydrogen bonding is generally much stronger than dipole-dipole. So sometimes that will be enough to figure out the differences in boiling points. We want decreasing boiling points. So that means we want the strongest intermolecular force down to the weakest intermolecular force. Well, methanol, which is CH.CH, methanol has an OH bond, and that is one of the 3 hydrogen bond possible compounds. If you have an OH, an NH, or an FH, those are all hydrogen bonds. So CH.CH should have the highest boiling point of all. So probably that means it's going to go first. I know that because CH4 is nonpolar, H2 is nonpolar. Nonpolar species have induced dipole forces working on them. So methanol is certainly going to be the highest boiling point, and it should go first. Now, between CH4 and H2, CH4 has a higher molar mass. Boiling is kind of about pushing things into the air. And because CH4 is heavier molar mass-wise than H2, probably CH4 is going to take a higher boiling point to make it boil relative to H2. So I would predict answer A is the correct one here, and that's what you see. Methanol is actually a liquid at room temperature, while methane, CH4, and H2 are both gases. But CH4 is quite a bit higher than H2. So even though CH4 and H2 had the same types of bonds, they were both induced dipole, and nonpolar, we would say that CH4 was higher because it has a bigger molar mass, takes more energy to get it into the gas phase than small H2. Here are 4 more compounds or elements, and it says rank the following molecules in order of increasing intermolecular forces. So on this problem, what I would do is go through and figure out what intermolecular force is working on each one of those. From there, you can put them in increasing intermolecular forces. This would be a good place to pause the video, work on it, and when you're ready, you can unpause it. We'll talk about the answer. Pause the video now. I'm going to assume that you've worked on the problem and you're ready to talk about the answer, so let's get through it. SO2 is a molecule, obviously, with a sulfur and 2 oxygens, and it might be tempting to think that it's nonpolar. But really, if you have a molecule like this, the best thing to do is to draw out the Lewis structure. And if you draw out the Lewis structure for SO2, you'll see that the sulfur has a lone pair and 2 bonds to oxygen. The lone pair on sulfur makes that molecule polar, all right? So SO2 would have, because it's polar, it would be dipole as its intermolecular force. It doesn't have any hydrogen, so it can't be H bonding, but it certainly is polar due to the lone pair, dipole. The second one, sodium chloride, it has positive sodiums and negative chlorides. And this is the ion-ion force. And this is one of the strongest forces out there. All right. In Chem 222 and 223, we're going to assume that ion-ion/metallic is the strongest force. So ion-ion is positive negatives. Metallic is just metals. We're going to assume that those are the strongest. That would probably be number 1 on the, that would be the biggest intermolecular force. CH.CH, we saw in the last problem, is polar with a hydrogen bond. So we would describe CH.CH as being hydrogen bonded. And helium is nonpolar and almost no mass. That's going to be induced dipole. So if you want these compounds and elements in order of increasing intermolecular forces, well, the weakest one's going to be induced dipole, helium. Then we would have polar dipole SO2. Hydrogen bonding would be next with CH.CH, and the strongest one of all, NaCl. If you put down answer C, you are good to go. So again, helium is induced dipole. SO2 is polar because of the lone pair on the Lewis structure for sulfur dioxide, so it's dipole. Methanol, CH.CH, is polar with hydrogen bonds, so we would say hydrogen bonds. And NaCl, strongest of all. So again, the overall force list is also there too. Induced dipole is the weakest. Induced dipole would be next. Dipole like SO2 after that. Hydrogen bonds. Ion dipole would be like Na plus in water. That's pretty strong. And then the strongest one of all, ion/metallic. When potassium chloride dissolves in water, what types of intermolecular bonds are formed? And there's all different kinds of them listed there. I will let you know that answer E is not correct. Bonds of matrimony, no one's getting married, but it's kind of funny sounding. Keep my day job. I know. Anyway, this would be a good place to stop the video, work on the problem, try and digest from my bad joke. And when you're ready to talk about the answer, you can unpause the video. We'll talk about it. Pause the video now. I'm assuming you're ready to talk about the answer to this question, so without further ado, let's do it. KCl by itself has ionic bonds, the positives and negatives, the K plus, the Cl minus. So by itself, it would be ion-ion. Water by itself is best described through hydrogen bonds. But for this one, we don't want either one of them separately. We want to know what happens when they come together. And so when KCl, like a lot of ionic compounds, dissolves in water, the ions break up and the ions become surrounded by water molecules, which is helping them to separate. And this, if you remember from the lecture notes, is an example of the ion dipole force. The ion dipole bonds are what would make this molecule possible, like why KCl dissolves in water. And it's a pretty strong force. It's not as strong as ion-ion, but it is stronger, generally people feel, than hydrogen bonds. Pretty cool. Which of the following should have the highest heat of vaporization, which is represented as delta H vap? And there are 4 possibilities, with also the possibility that they're all the same value. Probably not right. Anyway, see if you can figure this out. I recommend pausing the video. When you're ready, unpause it. We'll talk about the answer. Pause the video now. I'm assuming you've worked on it, you want to talk about the answer, so let's do this. If you see a question like this, all right, and remembering that this is a big section on intermolecular forces, most of the time, the strongest intermolecular force will have the highest whatever you're looking for. That's kind of a general rule of thumb, but it works amazingly more often than it doesn't. So what I would do with this problem is, first of all, I'm assuming I don't have a table of heat of vaporization values. And you can absolutely look this kind of stuff up on the all-powerful Google or in textbooks. But assuming we don't have it, then what I would do is go through that list, see if you can find the highest intermolecular force, because probably that's going to be a factor in the heat of vaporization. Vaporization means your liquid is turning into a gas, so you have to break those intermolecular forces to make that happen. So let's go down the list there. F2 is nonpolar. That would be induced dipole. CH.CH is hydrogen bonded. Water, C, is definitely hydrogen bonded. And D, ammonia, is actually hydrogen bonded as well. There's NH, OH, or OH bonds. But like we've talked about in lecture many times, water is kind of special because it has technically 2 OH bonds. So you have more effect usually from hydrogen bonding in water than you do the other hydrogen bonded species. So what I would do, again, without having access to a table, is I would guess that answer C is correct. And it is the right answer. So there's the actual values for the heat of vaporizations for those 4 compounds. And notice that F2 is the smallest because it's induced dipole. The other 3 are all much stronger. But again, water dominates. That extensive hydrogen bonding network makes these kind of things like heat of vaporization that much stronger. So again, if in doubt, look at the intermolecular forces. Strongest versus weakest will usually give you a good hint as to what the answer should be. Here's a unit cell for a compound that has copper and oxygen atoms. All of the gray copper atoms are within the unit cell. See if you can find the formula for the compound. So look at that picture carefully and remember the discussions we've had as to the types of unit cells. And I think that will help you to understand here what's happening. Anyway, work on the problem. When you're ready, you can unpause the video and we'll talk about the answer. But for now, to work on the problem, pause the video now. I'm going to assume that you've worked on the problem and you're ready to talk about the answer, so let's do it. This is the unit cell for an ionic compound. There are the kind of gray-black copper atoms, and there's the red oxygens. And we're trying to find the ratio of the copper to the oxygen. Well, it does say that all of the gray copper atoms are within the unit cell. And if you look at this, there's one right there. There's two right there, there's a third one right there, and a fourth one right there. So that means we have 4 copper atoms. Okay. Now, the red oxygens, if you look carefully, there are 8 oxygens in the corners. And we talked about on the simple cubic, body-centered cubic, face-centered cubic, how the corner atoms are 1/8 inside this cell. So of the 8 copper atoms I just put a highlight next to, each of those is 1/8 in the cell. So we have 8 times 1/8, 1 net oxygen atom from those 8 corner cells. And in addition, there's 1 copper atom in the middle there. It's in the middle of those gray kind of copper atoms, and that oxygen is certainly there. So that means that we have a total of 2 net oxygen atoms. We got 8 times 1/8 for the corners, and we have 1 atom in the middle. That's 2 net atoms. If you look at just the red atoms, it's really like the body-centered cubic cell we talked about, and that's kind of where I'm trying to lead you to on this problem. But anyway, you've got 4 coppers and 2 oxygens. And most of the time when it comes to ionic compounds, people want to think about the smallest ratio of whole numbers. They call that the formula unit. So if you divide the 4 and the 2 by 2, you're going to get Cu2O. This is copper 1 oxide's cell formula. This is what the unit cell looks like for copper 1 oxide. And you can actually interpret that using these kind of ideas. Remember that the outside corner atoms are only 1/8 in, but the one in the middle is totally in. No problem. This is an example of a phase diagram. Phase diagrams show all conditions where you have solid, liquid, and gas or vapor at different pressures on the y-axis and temperatures on the x-axis. And I'd like you to give me the name of the point at a pressure of 2 millimeters of mercury and a temperature of 54.34. And you can maybe see, but I'm just going to highlight it, that point is right there. So see if you can figure out the correct name of that point. Pause the video if you'd like to, and when you're ready to talk about the answer, unpause it. We'll talk about it. Pause the video now. At this point, I'm assuming you've looked at the problem, you want to talk about the answer, and let's do it. Okay, so assuming you just didn't default to E, the freak out point. All right, keep my day job. Yeah, no reason to freak out on this stuff. This stuff's pretty chill. It's not the freak out point, all right? You've got all those different possibilities, but the point where the solid, liquid, and gas or vapor come together is pretty important, and all substances in theory have it. And that point is called the triple point. The triple point is where all phases of O2 exist at the same time. So for oxygen's case, that would be 2 millimeters of mercury and 54.34 Kelvin, all right? To figure out normal boiling and freezing points, you go up to the 1 atmosphere value, which is 760 millimeters, all right? And freezing is where solids and liquids come together. That point right there would be the normal freezing point. It's where the substances freezes at 1 atmosphere of pressure, so that would be 54.8 Kelvin. The normal boiling point is also at 1 atmosphere. That's where the liquid starts turning into a gas. So for oxygen, that's 90.18 Kelvin. The critical point is usually a higher temperature and or pressure that the substance begins to do some unusual things. And we're not talking about that as much in Chem 222, but critical points, critical temperature, critical pressure, really usually relatively high amounts where the substances begin to do different things. So no freak out point, darn it, but you can figure out where the triple point is, woohoo, or you can find the normal freezing point and normal boiling point if you look at 1 atmosphere of pressure up there, 760 millimeters of mercury. Here's the phase diagram for oxygen once again, and I'd like you to figure out which of the statements below is correct. And it's a statement regarding the density of solid and liquid O2 at the same temperature. Okay, and there's 3 different possibilities. See if you can figure out which one is the right one. I recommend pausing the video. You can unpause it when you're ready to talk about it. Pause the video now. I'm assuming you want to talk about the answer, so let's do this. This question has to do with the density of solid versus liquid. And most substances, the density of the solid is greater than the density of the liquid. But with a phase diagram, you can confirm this. I'm going to remind you real quick about what the phase diagram for water looked like. And phase diagram for water looked something like this. And again, I can't draw, I apologize, but here's the 3 parts. What I'd like you to focus on here is the slope of the solid-liquid line. And for water, the solid-liquid slope was negative. But if you look at the solid-liquid line for oxygen, like most substances, the slope is positive. So positive slope means increases up to the right. Negative slope means, if you will, increases up and to the left. Positive slopes on a phase diagram mean that the solid has a greater density than liquid. So for oxygen, that's definitely the case. And if you look at answer B, the solid has a bigger density than the liquid density. So for this problem, we would say answer B is correct. However, water is really wild because ice cubes float on liquid water. And that means that the solid has a smaller density than liquid water. Water is one of the few substances that does that. Most substances are like oxygen, where the solid would sink to the bottom of the liquid phase. So solid oxygen and liquid oxygen, the solid oxygen would just sink to the bottom. But again, using the slope between the solid-liquid line on a phase diagram, you can confirm that. And that's kind of a cool thing to know. Here's a phase diagram for oxygen again, and the question is, what phase is oxygen found at a pressure of 1 millimeter of mercury and a temperature of 55 Kelvin? So see if you can use this example from this graph to figure this out. I recommend pausing the video. You can work on it, think about it, and when you're ready to talk about the answer, unpause it, and we'll do so. Pause the video now. I'm going to assume that you're ready to talk about the answer, so let's do it. Phase diagrams are pretty cool. They always show pressure and temperature conditions where you can have solid, liquid, and gas, vapor. Notice that plasma is not on this phase diagram. So plasma, which we'll talk about in the nuclear chemistry chapter, is a phase of matter, but it's a very high energy phase, and we wouldn't expect oxygen, at least in a normal phase diagram, to have a plasma component. In advanced courses, you might see phase diagrams which include the plasma state, but for right now, we're not going to see that. Anyway, to do this problem, it's pretty chill. What I would do is go up to where 1 millimeter of mercury is. So the bottom is 0, 2 is right there, so 1 is obviously kind of halfway in the middle. And then 55, you can see the numbers are getting bigger as you go right. I'm going to guess it's about right here. So if you go over to this point, this is the spot where roughly 1 millimeter mercury and 55 Kelvin come together. And you can see that this is in the lower part there of the phase diagram. This should be a vapor. All right, that's really all there is to it. It's pretty cool. Phase diagrams, pretty awesome for scientists that want to know the phase quickly without having to look up different conditions, pressure and temperature, stuff like that. Here's a question where we're taking liquid ethanol at 25 degrees Celsius and we want to turn it into a gas at 78.3 degrees Celsius. And to do this, we've got lots of different things we need. We've got the density of ethanol, we have the molar mass of ethanol, we have the boiling point of ethanol, we have the heat capacity of ethanol, and we have the heat of vaporization for ethanol. So there's a lot of pieces to this problem. Why don't you see if you can figure out which one of those answers it is? I'll be honest, it's not answer E. All right, darn it, 0 kilojoules would be so cool, but alas, that's not the case. Notice the kilo is a capital K. Anyway, I digress. See if you can do this problem. All right, this is going to be a two-step problem. You're going to have an MC delta T to heat the ethanol to 78.3, and then the second part will be mass times heat of something, where you need to figure out how much energy it takes to turn the liquid ethanol into a gaseous ethanol, and that's where the heat of vaporization pops in. So see if you can figure this out. I would pause the video, work on it for a little bit. When you're ready to look at the answer, unpause it, pause the video now. So I'm assuming you want to talk about the question, see what the answer is. So without further ado, let's do it. On problems like this, I try to break these problems down into small segments. And the segments will be, say, heating up the liquid or maybe turning the liquid into a gas. But I'll have a couple different answers. And at the end, I'll add them together to give you the overall answer. But another thing before we start, if you're going from liquid to a gas, all right, and you're heating a liquid up, both of those processes are going to take energy. Like you have to heat the liquid up, so that's going to only happen if you add energy. And if you turn a liquid into a gas, you have to break the intermolecular forces because we assume gases have no intermolecular forces on them. So both steps are going to be positive numbers. So right away in this problem, you can eliminate answer A, answer C, and the silly, if you will, answer E. Exothermic energies are not going to happen in this problem because everything we're doing is endothermic. The ethanol isn't going to heat itself, and it's not going to turn into a gas by itself. It has to have outside sources of energy. So the answer will be a positive number. The answer will be B or D. So that being said, what I would do is break this into some steps. So one step would be an MC delta T. This is where we're heating the ethanol. The delta T part would be 78.3 minus 25. That's the delta T part for heating up the ethanol. And the C will be the heat capacity value. That's the 2.44 number. The mass here, it says we have 1 liter. And there are 1,000 milliliters in a liter. So 1,000 milliliters times the density is going to give you the mass. And so I think that number, 1,000 times 0.7849, I believe it's going to be 784.9 grams. All right. That's the term that goes right there. So we have to use liters to milliliters to grams using density to find the mass. But that number times heat capacity 2.44 times the delta T, which is 78.3, the final point, minus 25.0, the initial point, that's going to give you Q1. That's the energy required to heat the ethanol to the boiling point. But we also have to boil the liquid, and that's going to be another M term, and that's the same process we talked about earlier where you take liters, turn to milliliters times grams. That's going to be the mass term, and we're going to multiply it by the delta H. Now, delta H, 38.56 kilojoules per mole. Well, there's two things about that. In the previous problem, the heat capacity was just joules. So we're going to have to multiply this number by 1,000 joules per kilojoules to make it add correctly to the first Q equals MC delta T. And we're also going to have to turn our mass into moles. You've got to get rid of everything but the joules part, but the energy part. So all of the mass stuff was in grams. We'll take the molar mass, turn it into moles. Moles times kilojoules per moles will give us kilojoules. And then because we're going to add it to something in joules, we're going to need to multiply by 1,000. So on this problem, you're just going to get a big number of joules. All of the answers, though, are in kilojoules. So we're going to have to divide by 1,000 joules per kilojoule again. We could have also turned MC delta T joules into kilojoules, that might have been a lot easier. When all is said and done, you should get 759 kilojoules as your answer. And again, let's see the parts. This first step right here is the Q equals MC delta T. I used the 1 liter. I turned it into milliliters, and then using the density, I got 785 grams. I used 3 sig figs because 1.00 liters is 3 sig figs. I then converted the Q equals MC delta T to kilojoules, which is probably more efficient, 102 kilojoules to heat up the ethanol. The second part, where we're actually turning the liquid into a gas, it's a mass times heat of something. So we turned the grams into moles using molar mass, multiply it by the delta H, 657 kilojoules to turn the liquid to a gas. And then finally, you add up everything to give the overall energy. It's definitely going to be endothermic, i.e. positive, 759 kilojoules. The energy that you're going to use to go from a gas at 78.3 degrees Celsius to a liquid at 25.0 Celsius would be the opposite of the answer we just had. So if you wanted to go from a gas at 78.3 to a liquid at 25.0, the answer would be negative 759 kilojoules, just the opposite of what we did. No problem. Breaking these problems down into little segments I find very useful, and I would recommend that you try that for yourself as well. Here's a question. We're dissolving 92.0 grams of ethanol, CH.CH into 270 grams of water. What's the mole fraction of ethanol in the solution? Mole fraction is moles of what you're looking at divided by total moles. We're going to use this data in several of the upcoming problems, so make sure that you hold on to the mole numbers. They might come in handy coming up. Anyway, see if you can figure out the answer to it. I recommend pausing it. You can unpause it when you want to talk about the answer. Pause the video now. I'm assuming you've worked on the problem, you want to talk about the answers, so let's do it. If you look at the answers in this problem and you think about what mole fraction is, there are two answers that don't make any sense. First of all, mole fractions can be no bigger than 1. So an answer of 2.0 doesn't make any sense at all. 2.0 would be outside of the range. The biggest number is 1. A mole fraction of 0 at the end could happen if you had no ethanol. All right, no ethanol would be no moles. You divide it by so many moles of water. 0 over something would be 0. E is possible if you had no ethanol, but we have ethanol, so answer E doesn't make any sense either. Mole fractions always go from 0 to 1. 0 means nothing. 1 means you have just that compound. So that's kind of an interesting thing. So what you want to do in this problem, turn 92 grams of ethanol into moles and 270 grams of water into moles of water. Then the mole fraction will be moles of ethanol divided by mole fractions of water plus mole fraction of ethanol. Make sure that you put the moles of ethanol in the denominator as well. Sometimes people tend to forget that. Ethanol is about 46.1 grams per mole, so 92.0 divided by 46.1, 2.00 moles. And 270 grams of water turned into moles using 18.02 grams per mole, 15 moles of water. So mole fraction of ethanol, 2 over 2 plus 15, i.e. moles of ethanol divided by moles of ethanol plus moles of water, 0.12. Make sure that you put parentheses around the denominator. All right, don't have it 2 divided by 2 plus 15. If you got an answer of 16, you're doing that. So you go back and you go 2 divided by parentheses 2 plus 15 parentheses, then you'll get 0.12 and you'll be good to go. Just make sure you do it. I'm trying to steer you right, not trying to lead you off in the wild wilderness. Cool. In this problem, same grams of ethanol, same grams of water. What's the weight percent of ethanol in the solution? Cool. So similar kind of problem. We'll talk about the answer in a little bit, but if you'd like to pause it, work on it, that's awesome. Unpause it when you're ready to talk about the answer. Pause the video now. I'm assuming you want to talk about the answer, so let's get into it. Weight percent, in this case of ethanol, weight percent would be grams of ethanol divided by total mass times 100%. Weight percent is the only one of these concentration units that's a true percentage. Answer E does not make any sense. A weight percent of 100% would be only ethanol. So if you had pure ethanol, then it would be good. But this one has water in it, so obviously that's not going to be the case. So mathematically what you do is you take 92.0 in the top and you would divide it by parentheses again 270 plus 92.0 parentheses, multiply it by 100%. And if you do that, that comes out to be 25.4%. All right, this is 25.4% ethanol. Cool. Percent water, you could take 270 divided by 92 plus 270 in parentheses times 100%, or you could just take 100% minus 25.4. So that would be an alternate way to find the weight percent of water. And the mole fraction of water, which I didn't discuss in the last problem, you could have gone 1 minus the mole fraction of ethanol to get the mole fraction of water. Lots of different ways to do it, and sometimes one way is easier than the other. Okay, same values as the last two problems, 92 grams of ethanol, 270 grams of water. What is the molality of ethanol? So see if you can figure out which one of those is the molality, the little M species. I recommend pausing the video, working on it, and when you're ready to hear the answer, unpause it. We'll talk about it. Pause the video now. I'm assuming you've worked on the problem. You want to hear how the answer goes, so let's do it. Molality, little m, moles of solute per kilogram of solvent. So in this problem, the ethanol is the solute. So you want 92 grams turned into moles of ethanol. And if you have that number from a previous problem, awesome. And if you don't, you can recalculate it, of course. But anyway, moles of ethanol divided by kilograms of water. There are 1,000 grams in a kilogram, so 270 divided by 1,000, 0.270 would be the kilograms of water. So moles of ethanol divided by kilograms of water. You can see there again that we have 2 moles of ethanol. If you didn't have it from before, that would be 0.270 kilograms. 2 moles divided by 0.270 kilograms, 7.41 molal. That would be the molality of this solution. Here's a problem. Same grams of ethanol, same grams of water, but we have the density of the solution is 0.9780 grams per milliliter. What is the molarity of ethanol in the solution? Okay, so molarity is different than molality. There are some parts the same and some parts different. See if you can do this one on your own. I recommend pausing the video, unpause it when you're ready to talk about the answer. Pause the video now. I'm assuming you've worked on the problem. You want to talk about the answer. Let's do this. Molarity is moles of solute over liters of solution. Okay? Now, the moles of solute, moles of ethanol, you calculated in the last slide and also on the mole fraction slide. I think it was 2.00 moles of ethanol. That's the number that's going to go in the numerator. But in the bottom, you need liters of solution. So what scientists usually do is they find the total mass of the solution. So that would be 92.0 grams of ethanol plus 270 grams of water. Add those two numbers together. That's going to be the mass of the solution. Remember, solution is solute plus solvent. So 92.0 plus 270 gives you mass of solution. Okay, the 0.9780, that's the density of the solution. So to the mass of ethanol plus water you got earlier, you want to divide it by the density of the solution. That's going to turn your mass of solution into a volume of solution, the milliliters of solution. And once you have the milliliters, you can divide by 1,000 to turn it into liters of solution, so that the moles of ethanol, which I think is 2.00 moles, you'll divide that by the liters of solution to get the answer. Now, one hint, molality is usually usually a bigger number for the same set of conditions than molarity. So in the last problem, I believe the molality was 7.41 molal. The molarity will be a number bigger, or it will be a number smaller than that. So if it was 7.41, there's no way the answer is going to be C. All right, molarity is almost always smaller than molality. So if you do the math, all right, here's all the fun stuff. You can see, first of all, there's 2.00 moles of solute. That's going to go in the top part of molarity. Then you add up the 2 grams, the solvent plus solute, to get grams of solution, 362. You divide that by the density. This is the only time you need density to find the milliliters of solution, which is 370 milliliters. That's 0.370 liters. So 2.00 moles divided by 0.370 liters, 5.41 molar. And again, usually molarity is smaller than molality. And this number 5.41 is certainly smaller than the previous 7.41. Good to go. In this problem, an aqueous solution of ethanol has a solution density of 0.9163 grams per milliliter and a concentration of 0.801 molarity. What is the mole fraction of ethanol in the solution? Okay, so in this problem, you're going from a molarity to a mole fraction. Anytime you go from molarity to mole fraction, weight percent, or molality, you need that density of the solution, or if you're going the opposite direction. So we didn't need a density in the first problems, but when it comes to molarity, we certainly do. See if you can figure out this answer on your own. I recommend pausing the video. You can work on it. When you're ready, you can unpause it. We'll talk about the answer. Pause the video now. I'm assuming you've worked on the problem, you want to check it out, so let's discuss it. All of these kind of questions have a good assumption as a starting point. And when it comes to molarity and you're shifting it into mole fraction, which is what we're doing, or weight percent, or any of those kind of things, what I would do is I would assume you have 1 liter of solution. If you have 1 liter of solution, that means a couple of things. It means, first of all, you have 0.801 moles of solute, which is 0.801 moles of ethanol. And you also have 1 liter total, which is 1,000 milliliters. So from 1,000 milliliters of solution, you can use that density to get the total mass in grams of the solution. All right. So 1,000 milliliters times 0.9163 grams per milliliter will give you the grams of solution. That equals grams of ethanol plus grams of water. Now, if you know that you have 0.801 moles of ethanol, which by the way we'll use in mole fraction here in a little bit, you can turn moles of ethanol into grams of ethanol using the molar mass. So 0.801 moles of ethanol times the molar mass will give you the grams of ethanol. And you can subtract that number from the total mass of solution to find the grams of water, the solvent. And from grams of water, you can go to moles of water. So mole fraction of ethanol will be moles of ethanol, 0.801, divided by moles of ethanol plus moles of water. So looking at the math then, what I would do again is I would assume exactly 1 liter of solution, which is 1,000 milliliters. All right. And in a liter, that means 2 things. Number 1, and a number we're going to use a lot, 0.801 moles of ethanol. And if you look down at the very bottom, that's where that number pops in. But the other thing it says is you have 1,000 milliliters of solution. The density and the volume you can turn into the mass of the solution, which is that number right there. Now, in the solution, we don't know how much of the grams are water and how many grams are ethanol, but we can calculate the mass of the ethanol. 0.801 moles times the molar mass gives you 36.9 grams of ethanol. So 36.9 subtracted from 916.3, you get 879.4 grams of water. And then finally, because we want moles of water, grams of water divided by molar mass of water will give you the moles of water, 48.80. So mole fraction, moles of ethanol divided by moles of ethanol plus moles of water, 0.0161. Wow. So it's kind of a heavy-duty process for this type of problem, but it is stuff you can do. Just keep isolating. Remember, if you start with molarity, always assume 1 liter of solution. If you start with molality, you assume 1 kilogram of solvent. If you start with mole fraction, assume 1 mole total. And if you start with weight percent, assume 100 grams total. All of these things together will get you to where you need to go. The steps sometimes are strange. If you're needing more practice on this, there's the solution concentrations handout, which is a series of work problems like this where it helps you start with right kind of assumptions, stuff like that. If you don't know where that is or you don't have that handout, please email me. I'm happy to help you out and get it, no problem. This is all stuff you can do. The Henry's law constant for nitrogen in water at 50 degrees Celsius, 53 degrees Celsius, 8.4 times 10 to the minus 7th molar per millimeter of mercury. The vapor pressure at 53 degrees water is 107 torr. So it says find the equilibrium concentration of N2 in water if the total pressure is 1 atmosphere. All right. Now the 107 torr number is going to be important. That's the contribution of water's vapor pressure to the total pressure. And remember, the total pressure is 1 atmosphere. So see if you can use all this information to find the right answer. I recommend pausing the video, work on the problem, and when you're ready to talk about the answer, unpause it. We'll talk about it. Pause your video now. I'm going to assume that you've worked on the problem and you're ready to talk about the answer. So without further ado, let's do it. First of all, a question on units. We've got atmospheres, torr, and millimeters of mercury. An atmosphere is equal to 760 millimeters of mercury. So when it says 1 atmosphere, you can think 760 millimeters of mercury. A torr is equal to 1 millimeter of mercury. So if you want, you can recreate 107 torr and say it's 107 millimeters of mercury, and that's fine. So it might be tempting to take 760 millimeters of mercury, 1 atmosphere, and multiply it by the Henry's law constant to get one of the big M numbers. But the thing is we want just the pressure, the reflection, how much solubility we have for nitrogen. We don't want the water. And N2 in water is definitely a volatile liquid, like it has an appreciable vapor pressure. However, if the total pressure is 760 millimeters of mercury, i.e. 1 atmosphere, and water contributes 107 millimeters of mercury, i.e. 107 torr, to it, then the pressure of N2 will be 760 minus 107. And whatever that number is, that reflects the pressure of the nitrogen in millimeters of mercury. We'll multiply it by Henry's law constant, get some kind of molarity, and be good to go. So mathematically, all right, first of all, subtract the water vapor pressure from the total pressure. And 1 atmosphere is 760, a torr in millimeter of mercury the same. So that means you have 653 millimeters of mercury pressure for nitrogen at this specific temperature. So the solubility, according to Henry's law, is going to equal that strange Henry's law constant times 653 millimeters of mercury, the pressure of just the N2. And you can see how millimeters of mercury cancel. You'll have just big M left over. 5.5 times 10 to the minus 4 molar is the concentration of the N2. So most of the time, Henry's law is pretty chill. You've got to know atmospheres, millimeters of mercury, torr, stuff like that, but that's not too bad. Make sure that you do have just the pressure of the gas you're looking for using the solubility Henry's constant. You wouldn't want to use a whole atmosphere here. You want to subtract out the water, but pretty chill. Here's a question. We've got 0.0400 moles of iodine dissolved in 1.96 moles of carbon tetrachloride at 65 degrees Celsius. Now, carbon tetrachloride is a liquid, and it does have a vapor pressure. If it's pure CCl4 at that temperature, the vapor pressure is 504 millimeters of mercury. But we've added iodine to this thing to make a solution. Hint, hint. What's the vapor pressure of the carbon tetrachloride over this solution? This is an example of Raoult's law. See if you can use this information to find the right answer. And so what I recommend, pausing the video. We'll talk about the answer afterwards. Pause the video now. I'm assuming you've worked on the question. You want to talk about the answer. Let's do this. Okay. Raoult's law says that the vapor pressure of a solvent over a solution is less than the vapor pressure of the pure solvent. Okay. So the 504 millimeters of mercury number, that's the vapor pressure of pure CCl4, i.e. CCl4 without iodine. As you add iodine solute, the iodine will block the liquid CCl4 from getting into the gas phase. That's going to make less pressure. So the answer we're going to have, the vapor pressure in the solution, the solvent in the solution, is going to be a number less than 504. So if you look at these answers right here, definitely not A, because it has to be less than 504. It will definitely not be more than 504. It's going to be C, D, and E. And I would love to say answer E, but no, that's not the right answer. It's all stuff you can handle, I promise. I'll keep telling you that. If you forget, you email me and I will tell you again. Anyway, it's going to be C or D. Now, I'll be honest, the solvent is usually pretty massive in how much its quantity is. I would not predict answer D. I would predict answer C. But let's talk about how you can actually get the right answer. Raoult's law, mole fraction of solvent, not solute, but solvent, times vapor pressure of pure solvent. So mole fraction of solvent will be moles of CCl4, which is 1.96. We'll divide that by total moles, 1.96 plus 0.04. That's going to give you mole fraction solvent, and we'll multiply that by vapor pressure of pure solvent, so times 504. So if you do this, vapor pressure of solution, solvent in solution, equals mole fraction solvent times vapor pressure pure solvent. VP with a little 0 by it, that means pure solvent in chemistry world. So mole fraction of solvent, CCl4, moles CCl4 divided by total moles, so 1.96 divided by parentheses, 1.96 plus 0.04, that comes out to be 0.980. Don't use mole fraction solute here. It's mole fraction solvent. But anyway, 0.980 times the pure vapor pressure of 504, vapor pressure 494 millimeters of mercury. So again, this is Raoult's law, mole fraction of solvent times vapor pressure of pure solvent. Good to go. Here's a boiling point elevation question, and it says, what mass of ethylene glycol is a diol, there's the molar mass too, must be added to 125 grams of water to raise the boiling point by 1 degree Celsius. And you'll need a boiling point constant for water. That number is 0.512. So see if you can figure out which of these is the correct answer. Unfortunately, answer E is not right. Pause the video, work on it. When you're ready to talk about the answer, unpause it, pause the video now. I'm going to assume that you're ready to talk about this problem after working on the question. So let's see what's going on. The main equation for boiling points, delta T equals K times M. The K number is right there, 0.512. Delta T is how much the boiling point has changed. And in this problem, the change in boiling point, 1.00. So that means that the solution, we want it to boil at 101 degrees Celsius. Water normally boils at 100 Celsius. The difference between those would be 1. So 1 equals 0.512 K times M. The first thing to do would be to solve for M, molality. Molality is moles per kilogram of solvent, and we have 125 grams of solvent water here. So that would be 0.125 kilograms. So molality times kilograms will give you just moles of solute, which is moles of ethylene glycol. And moles of ethylene glycol times 62.0 grams per mole will tell you how many grams you need to add here. So let's look at the math without me just talking about it. Delta T equals K times M. Oh, I didn't include I. I is the Van Hoff factor. Van Hoff factors are useful when you have ionic compounds. So positives and negatives like sodium chloride or potassium nitrate. If you have something organic, i.e. covalent bonds, which is what ethylene glycol is, I is considered to be just 1, so you can ignore it. But anyway, the first step there was to solve for molality, delta T divided by K, 1.95 molal. You multiply moles per kilogram by kilograms of water to get the moles of ethylene glycol, which is 0.244 moles. And finally, that times molar mass ethylene glycol, 15.1 grams. So what that means is that if you put 15.1 grams of ethylene glycol in 125 grams of water and stirred it up to make a solution, your boiling point would go from 100 degrees Celsius to 101 degrees Celsius. You have raised the boiling point by 1 degree Celsius. I mentioned quickly on the last problem about the Van Hoff factor, and the Van Hoff factor is very useful when you have an ionic compound. So in this question it says, which of these water-based solutions is expected to have the higher boiling point? So see if you can figure out which one of those is the right answer. Pause the video, and when you're ready to talk about it, you can unpause it. Pause the video now. I'm going to assume you've worked on the problem and you want to see what the answer is, so let's talk about it. This question is another delta T equals K times M times I. I'm going to throw that in there. Now, K, the boiling point constant, is going to be the same. K depends on the solvent, and since they're both water, K will be the same in both cases. So delta T equals K times M times I. K isn't really a factor. M is the molality, and you can see that sugar here is 0.15 molal. That's a bigger molality than 0.10. So initially, you might say B is the best answer here, because higher molality, higher boiling point, and that's true. If it was just molality, sugar would be it. But it's also delta T equals K times M times I. Organic things like ethylene glycol in the last problem or sugar in this problem are just big covalent bond molecules, and they don't break up into positives and negatives. On the other hand, NaCl is ionic. It's going to have a positive sodium and a negative chloride. 2 ions are going to come from 1 mole of NaCl. And because it really just matters how many pieces you have, there's going to be 2 pieces per NaCl. I factors account for these numbers of ions. So for A, the I factor would be 2 ions per NaCl. On B, the I factor is just 1. All of these covalent things have just I values equal to 1. So K times M times I, K doesn't matter. M times I for A would be 0.10 times 2. On B, M times I would be 0.15 times 1. So 0.10 times 2 is bigger. We would predict that answer A would be correct. The sodium chloride, with its greater dissociating set of ions, should create a higher boiling point than the sugar. Sugar just breaks up into 1 piece. So I factors become really important for ionic compounds. They will change your distribution quite a bit. So here's a question, 29.3 grams of sodium chloride, hint, hint, ionic, anyway, molar mass 58.5 grams per mole. It's dissolved in 500 grams of water, and the question is, what is the boiling point of this solution? And there's the boiling point constant again for water. So see if you can figure out which of those is the correct answer. In a little bit, we'll talk about it, but pause the video now and work on it first so the answer makes more sense to you. Pause the video now. I'm going to assume that you've tried the problem and you want to talk about the answer, so let's do it. So in this problem, I would use the full version of the equation. Delta T, which is what we're after, equals K times M times I. Okay, well, K is easy, 0.512. Molality, we need to take the moles of NaCl and divide by the kilograms of water. So 29.3 grams divided by 58.5 grams per mole, that'll tell us the moles of NaCl. And we'll divide that by the kilograms of water. So 500 divided by 1,000, 0.500 kilograms. Whatever that is, that's going to be the molality. But we've got one more piece here. We have the I factor. I factor is important here because, again, we have an ionic solute. NaCl will break up into Na plus and Cl minus ions. So the I factor here is going to be 2 in this problem. So K, 0.512, times molality, whatever that is, times 2, that's going to give you the delta T. And we'll take that delta T and add it to 100 degrees Celsius, the normal boiling point of water, to find the right answer. So on this problem, molality is the part I would start focusing on. Find the moles of NaCl, divide by 0.500 kilograms. That comes out conveniently to 1.00 molal. So then delta T, this step right here, K times M, 1.00, times I, which is 2, 1.02 degrees Celsius. So the boiling point will go up by 1.02, 100 plus 1.02, boiling point 101.02 degrees Celsius. Here's a compound called erythritol. It occurs naturally in algae and fungi. A solution of 2.50 grams of erythritol and 50 grams of water freezes at negative 0.762 degrees Celsius. So what is the molar mass of this compound? Here's the freezing point constant for water, negative 1.86. Now look, on a problem like this, you've got a lot of negatives floating around, but here is a punchline I want to talk about right now, because mass in chemistry, grams, all right? Grams can never be negative, and grams lead to moles, moles lead to molality, molarity, grams per mole, all these kind of things. So whatever you do, get positive moles, positive molality, stuff like that. Make things absolute value if it makes it easier. But anyway, using this information, you can calculate the molar mass of erythritol. Try this out. All right, pause the video, work on it. When you're ready, unpause it. We'll talk about the answer. Pause the video now. Assuming you've worked on it, you want to talk about the answer, so let's do it. I want to highlight again, you want to make sure molality, moles, grams, molarity, all these kind of things, they're never negative, not in chemistry. That's a real cool thing, I guess, about chemistry. It's not very exciting science fiction-wise, but that's another story. So in this problem, you've got a negative KFP and a negative freezing point. All right, just realize you've got to end up with positive numbers. So freezing points are lower than the solvents they come from. The delta T on this problem, again, I'm kind of a positive number person. I would just absolute value everything here. So the freezing point will have a delta T of positive 0.760, and the freezing point constant, absolute value, once again, 1.86 positive. That'll ensure that I get a positive molality. Now, sometimes freezing point constants are already positive, and they assume that you know that molality has to be positive. But again, the punchline, the most important thing, make sure your molality, molar masses, moles, grams, those numbers are always positive. So delta T equals K times M. K, I would use 1.86 positive. Delta T, I would use positive 0.762. 0.762 equals K times M, 1.86 times M. I is going to be 1 here. Erythritol is something with algae and fungi. That's going to be biochemistry / organic chemistry. And basically everything there is organic and covalent. So I would just assume I factor is 1. But anyway, you'll solve for the molality, the moles per kilogram in this solution. You can multiply by the kilograms of water. So 50 grams divided by 1,000, 0.0500 kilograms. That'll give you the moles of erythritol, and then grams per mole, 2.50 grams divided by the moles of erythritol we just calculated is going to give you to the answer. So in this problem, all right, first of all, assume I is 1 because it's organic and stuff like that. Notice the way I did it. Delta T divided by K, the negatives cancel out. You could also just absolute value the whole thing. Doesn't matter. But the important part, make sure this number is positive. If you get a negative, just like stop the problem right there, all right? Make sure molality and molarity and moles and grams and number of molecules, those kind of things, those things are always going to be positive numbers in chemistry. So anyway, positive 0.410 molal by any means necessary. Now, multiply that by the kilograms of water, 0.0500 kilograms, that's 50 grams divided by 1,000 to get the moles. That goes down here. You've then got the grams from before, molar mass erythritol, 122 grams per mole. Osmotic pressure is another one of the colligative properties that's especially useful when it comes to biochemistry and biomolecules, stuff like that. Anyway, we've got insulin, 20 milligrams dissolved in 5 milliliters of water at 300 Kelvin. And that kind of condition provides an osmotic pressure of 12.5 millimeters of mercury. So the solution actually goes up by 12.5 millimeters of mercury in a U-tube or something like that. Anyway, let's use this information to calculate the molar mass of insulin. So pause the video, work on this, and when you're ready to talk about the answer, you can unpause it and we'll do it. Pause the video now. At this point, I'm assuming you're ready to talk about the answer to this question, so let's get into it. So osmotic pressure gets the symbol pi. Pi equals ICRT if you include the full version. Now, the I factor here is not so important. Anytime you have a biomolecule, insulin or something like that, or vitamin C or whatever, caffeine for that matter, all of those are covalent and I is just one. So you can ignore I on this problem. You don't have C, and that's what we're going to be solving for. And C is the moles per liter, the molarity of this solution. But R, 0.082057, you've got that. T is the Kelvin temperature. That's 300 Kelvin. Notice the 3 sig figs. And pi is literally the osmotic pressure. And when you put it into the equation, it has to be in atmospheres. We have a millimeter of mercury atmosphere pressure, or osmotic pressure. We can take 12.5 divided by 760, and that will give the osmotic pressure in atmospheres. We'll solve for C, which is the moles per liter. We want to get moles kind of by itself. So if we multiply moles per liter by 5 milliliters in liters, so 5 divided by 1,000, that's going to give us the moles of insulin. And then finally, grams per mole is the molar mass. We need to convert 20 milligrams into grams by dividing by 1,000. It's going to be a small number of grams, but that's going to give us one of the answers down below. So let's look at the math. Again, pi equals I CRT. I is just one. Everything is covalent. We're first going to solve for C. We do need to get pi in the right units. So 12.5 divided by 760, 0.0164 atmospheres. That's the pressure of the osmotic pressure in atmospheres. Then the C, the concentration, is that pressure divided by I R, 0.082057, and T in Kelvin, 300. We get there the almost devilish looking number, 6.66 times 10 to the minus 4 molarity for the concentration. We'll multiply that by the volume of the solution. So 5 divided by 1,000, 0.00500. We get this number, the moles of the solute insulin. 20 milligrams divided by 1,000 is 0.0200 grams. That divided by the moles, 6,010 grams per mole. Woohoo! That is a big molar mass in my world. Most of my molar masses of regular chemistry, 500-ish grams per mole would usually be pretty high. So this is 6,000 grams per mole. Wow! These molar masses really blow my brain. But with osmotic pressure, you can figure out these values pretty readily, and that's one of the major advantages to knowing about osmotic pressure. That's the end of this review. I hope this review helped you and it'll help you prepare in your studying for the actual midterm exam. If you need more practice on any of this stuff, let me just advertise. There are a series of practice problem sets that you can look at. You can go back over the relevant problem sets to see some answers, and the answers are provided in the back of the practice problem sets. There's also concept guides and chapter guides, which will help you. Concept guides are worked problems from the different chapters, chapters, and chapter guides are online compendiums of different information from the website that also might assist you with your studying. Each chapter has end of chapter problems in not only the textbook, but actually at the end of the lecture notes for my PowerPoint lectures as well. And I do encourage you to check them out. The answers are given at the end of my lecture notes, or every other problem has the answer at the end in the problem set book. And so either way, you've got lots of possibilities to check it out. I wish you the very best with your studying. And if you do have any questions, be sure to email me. I'm happy to help. Have a wonderful day and good luck on your exam.